on it.
Or we can just go to Lowe's and buy Christmas tree and throw it off the roof.
All right. So the first thing that I want to do, 5.1 homework. I haven't checked. I don't know up to date. I don't know if everyone's gotten it. When I checked a couple days ago, not very many had completed that. We had work time last class to do that, right? Was that the end of last class?
Mm-hmm.
Right?
Yeah.
I don't know. I was trying to help everybody. I don't know if everyone else was super focused on it. But I wanted to start and say, hey, any overarching questions on that homework? Was there one problem that you did that was like, man, I didn't even know where to start for this problem? Anything like that? Any questions on 5.1 homework that we can talk about? Right? Particularly if there was a problem that was like, this was absurd. I don't think this is possible. Questions like that I want to talk about as a whole. Any I guess, question, comment, concern about 5.1 homework? Anything? If not, that's okay. I hope it's because you actually don't have any questions. You know, the ones you missed, you were like, oh, duh, that was stupid. If it's because you didn't do it, that's a different issue. That's you need to buckle down and get your work done, right? If you don't, that's 100% your choice. I think it's a silly decision, right? You're purposely choosing to get a 0, and you're not practicing, right? The whole point of this is to get this material, understand it. We're off to a good start. You got to just keep on it, right? Keep up. So again, any questions about that homework? Does anybody have any that they did that they want me to go through and work through? Or are we golden? We good? Okay. Again, that assignment, there's a couple, really intro questions, but also, a couple of them they're from AP, right? So even the wording, it's going to be a lot like AP, right? If they're tricky, don't be disappointed that you can't get 100%. Right? One thing to think about, I had a Zoom meeting late last night with other physics teachers in Indiana, and one of them reminded me that, hey, on the AP test, it's made to be very difficult, right? He was saying in his experience, he's taught it for years, if you know forces, basic motion, energy, and momentum, if you got those concepts, those 4 units down, you could probably pass the AP test with a 3. He's saying if you know 4 out of the 10 units, you could probably get at least that 50% to get that middle-of-the-road 3 and pass. Because those topics are so important. Right? That's why I was emphasizing energy. Remember, again, I still haven't asked custodians if I can tape or whatever. Energy is 16 to 24% of the test. So it could be that a quarter of the AP test is energy questions. 1 unit. Right? That's part of what I want to strategize with you that day before we go to break, is start thinking, okay, what are these things that I really got to make sure I know? Kinematics and dynamics, each of them are about 15, 20%. Those 3 units, half of the AP test. Right there. The one we're in now, momentum, 16% of the test. Momentum's a really big one. So part of that is to say, hey, there are some topics that are fundamental to physics. Energy, momentum, those are key. The forces, stuff like that. Another thing he mentioned is certain questions might be a possible, like the free response questions, FRQs. The highest score you could earn is like, say, 7 points. And they run the AP test, and the national average would be like 0.9 points. The average across all test takers was a 0.9 out of 7 points. That's pretty normal for certain questions on the AP test. Those are the questions that differentiate the 4s and the 5s. Right? The kids that do well on those really tough questions, they're the ones that are getting those 5s. But if you only get a 2 or a 3 on that question, don't think about it as a 3 out of 7. Think about it as, holy smokes, I did twice as well as the national average.
And I just got.
There you go. Right? So I want to share that with you to give you guys, again, Evan, can you make sure you got your mask on, please? I want to share that to give you that context, right? These unit tests, if I make them easy, it doesn't help you, right? It'll make you feel good and your grade look good, but this final test, you might do terribly, right? So I'm trying to find a happy medium in my testing where half of it I do, okay, basic concepts. We got to know it. They should be these easy questions. The other half, I'm going to try and pull straight from AP. I want you to experience the level of difficulty that is going to be on that AP test. So that means if you get your test score back and you're like, oh crap, 20 out of 30, that's terrible. That's almost failing. Like, okay, yeah, by the numbers. You know, I'm doing test corrections to help make that look better so it's not hurting your grade and you're not stressing. But in reality, I mean, if you're doing better than 60% of, you know, you're past the average, that's passing the AP test, right? So I want to at least throw that out, put that in your back of your mind, right? You're not going to get this perfectly the first time. You're really not supposed to. That's not how the material is made. It's made to be challenging to every single person. No one should ace it. So I want to stop talking about that. 5.1. I want to finish the momentum notes, at least finish momentum and impulse, right? We finished talking about what an impulse is and how they relate. I want to review that a little bit. Give some more examples of that, and then talk about systems, right? Systems never go away in physics. That's how we define like what we're interested in for a question. We're going to talk about systems and how they impact a momentum problem. So I'm going to cue this up. I got it. Is that projecting? There it goes. Where did we leave off? Oh, here. Yeah. Oh, it's up on yours, but not mine. There. Okay, so, quick review. What's momentum equal to? Mass and velocity, right? What is the letter we use for momentum? Yep, it's a P or rho. I do the rho, the cursive P. Lowercase p, I think, is what College Board in your equation sheet will do. Hi there. Like a couple minutes, quick? Yeah. Yes, that's fine. So momentum is lowercase p, mass times velocity. That's what momentum equals. What happens if you have a change in momentum? Let me ask you a better question. What causes a change in momentum? Impulse. Good. How do you calculate an impulse? What is an impulse?
Force times time.
Good. Force times time. When you apply a force over a certain time, that is an impulse. If you apply an impulse on any object or system, you will change the momentum by definition. Remember our momentum equals m delta v. Wait. Delta v, I'm saying my variable's wrong. Delta p, a change in momentum, is caused by your object having a change in velocity, m delta v. What caused that change in velocity or change in momentum? It was your impulse, F delta T, right? So, just going to play. Wait a minute. My Nope.
There's no slide up on the whiteboard.
Come on. Oh, for goodness sake. Some struggle. My goodness. Okay. So 2 scenarios. Guys, phones away. I don't want to ask you again. Please, please. This is part of the issue that I had with my last class that I had to go talk with Miss Rush with for half an hour. Give me your focus, give me your attention, let's get through this, please. 2 scenarios. You got these 2 guys falling. One's falling on a bed of bricks, one's falling on a giant foam mattress. Right? They exaggerated the motion because when you hit the bricks, you just stop. Right? Makes sense. On a mattress, you got a soft landing. Right? That mattress compresses and then stops you. Think about it carefully. Which scenario was there a larger impulse? You gotta be careful. Take a moment before you blurt out an answer. What is an impulse?
There
are a couple answers.
The mattress because of the larger time. Same force.
Oh, can you guys see now?
Yeah.
Okay.
Sure.
Okay. So, an impulse is a force multiplied by time. How long the force is applied. So you're saying this one had a longer time. Okay? Aiden, what's your thought?
I was thinking bricks. Now that I think about it, I'm not really too sure.
Okay, that's okay. I want to ask you another question. I asked the question, what has a larger impulse? What does the impulse cause? A change in which scenario had a greater change in momentum? They both had the same mass or falling at the same velocity, and they impacted the same height. But which person changed their momentum more?
The guy on the bricks because he all of a sudden stopped, where the mattress he slowed.
Be careful.
But they both end up at 0. Their change of momentum.
The moment they touch the surface, they have a certain velocity, and it's the same. They're identical guys, identical fall. What is both of their final velocities? 0. They have the exact same change in velocity. So delta V is the same. It's the same guy, so their mass is the same.
So their impulse has to be the same.
So they have the same change in momentum. If they have the same change in momentum is your impulse. So guess who had the larger impulse?
Neither one.
Neither.
Because the bricks have more force much different time.
Yes.
Gotcha.
It's really counterintuitive. That's why I wanted you to stop and think about it. True. Aiden said, hey, one guy's got a broken back. Right? This is the reason that momentum is useful to think about. Right? This is why really strong, quick collisions are dangerous. Right? You might go from, right, when you hit a brick wall, you come to a standstill, that hurts. Well, wait, my car was only going 20 miles an hour, but it stopped instantly. Huge force on a really short time scale. to reduce my momentum to 0. But what happens if I hit the brakes and I slow down? Am I hurt in that situation? My change of momentum was exactly the same.
Like tripping on your seatbelt.
Yeah, but the force was really small and it occurred over a long time. My body can easily withstand the force of my seatbelt tugging on me. It can hold that all day long, right? That's a great point, Aiden, because these scenarios, same physics, but the result's different. That's why this is useful, right? Collisions is the best way to think about, like, what the heck do we do with this stuff? And again, you can do the math and see. Same mass, same velocity. Same mass, same velocity. They have the same momentum coming in. They both come to a standstill, so the momentum goes to 0. To your point, Aiden, which person experienced the larger force?
Okay.
This guy. Massive force really quickly to change his momentum. That hurts. Other guy, really slow force, who experienced the larger time of impact? This guy. The impact was spread out as that mattress compressed. Really small force for a long time to bring him to that stop. Okay? So one, I want you to think about, okay, there's utility, there's value in knowing momentum, right? If you really get into it and start thinking about it, everywhere you look, especially in a car, you can think about like why this is valuable to know. This is what we just saw. Exact same impulse. One of them had a massive force really quickly, teeny tiny amount of time. The other one, exactly the same thing, but a little force for a long time. They're doing the exact same impulse, the exact same change in momentum, but they are different, and then therefore the results are different. Do you know this physics concept is why we have airbags? Right? Would you rather a, thin padded steering wheel stop your momentum? Or would you rather have a cushy airbag stop your momentum?
Airbag.
Okay, why?
Because larger time means lower force.
Right. The point of this is it's going to bring you to a stop. You hit a wall, your body's moving forward, something's got to stop you. Your momentum has to go from whatever it started to down to 0. I would rather an airbag do that really slowly and gently on my body rather than smashing into the steering wheel column. Yeah. Right? You'll smash the steering wheel and the steering wheel column will pierce you because you have a massive force all of a sudden. Right? Airbags exist because we understand momentum.
You gotta wear your Kevlar vest.
Huh?
So you gotta wear your Kevlar vest.
That I don't think would help. Kevlar vests stop punctures.
You said, like, steering wheel would puncture you.
Okay, in that situation. But even if it did stop the steering wheel column, you still get hurt more.
But wouldn't that still protect you more than not having it?
It would. It would, but
over.
the change of momentum, the effect of that is still that bad.
Yeah.
True, you create a barrier that
Well, I was
stops
thinking,
penetration,
if it hits
but
it,
the force
wouldn't
is the same.
I mean, wouldn't it press more like it'd be a more spread out spot than just like
It
bam,
would.
all in the
It
center?
would. The reason it does that, that's what prevents penetration. If you
Yeah.
spread the force out, your body can absorb it. So that's a Kevlar vest would help, but you still, that blunt force, you're taking all of it.
Yeah.
Right? Say it's 10,000 newtons, you take all of that. It just disperses it better. But it still happens that quick. The airbag gives you that nice small force for a long period of time to gently slow you down.
Just drop a tank.
Yeah, you're not just coming to any quick stops.
I mean, that's what GTA is talking.
You stop in half a second with an airbag. Sorry, half a second is the time it takes for the airbag to stop you. 0.05 seconds, 5/100ths of a second is the time it takes to stop you by the steering wheel. right? Look at that. 10 times less force using an airbag. And you can think, hey, 2,000 newtons of force, how much will there be with the airbag? Well, 10 times less, right? This times this is your impulse. That's a constant value because you're going from a certain speed down to 0. This is equal to half a second times what? Well, 200. 10 times less force. Same physics, same thing, but your impulse is, created differently. I thought that was a video, but this is an interesting thing. Anybody do rock climbing? A little bit? I don't. I can think about basics, but apparently there's different types of rope. Do you see the varied threads? There's different types of threads in a dynamic rope. Static rope, it's pretty much just solid threads, right? You can't stretch it. It's snug because you're not moving. It holds you there. You want it to be taut and stiff. You don't really care. Over here, if you accidentally fall, do you want a stiff, unflexing rope to stop you? It's going to stop you like that. All of your force falling will be stopped in an instant. Yeah, that's how you get whiplash and snap your neck, right? Very dangerous. So, dynamic rope, to my understanding, has solid threads, but it's got elastic threads mixed in. So when you fall with dynamic rope, the line goes tight, that rope bends and eventually stops you. Right? It gives you more time to slow you down. When it's doing that, the impulse is the same, but you're increasing the time that force is applied, and the force is a lot less. It's much gentler on you. This is another reason, right? Most people, consumers, they don't know the physics of this decision. They just know from experience. Hey, if you're doing something where you could fall, you need dynamic
So
rope.
stretchy and stiff.
Yeah, that's all the consumer would know. But the engineer that made this, they know physics. That's why they made it that way, right? That engineering is using science to make things and accomplish things.
It's a trick question. You still have the rule.
Ah, yes, of course.
This is the same thing. Let's see.
I mean,
So
I'd rather-
there's an activation force, right? The strength that it's supposed to elongate or soften an impact, guys. So at 550 pounds, this harness will activate and basically turn elastic. So it'll start slowing you down slowly, and its maximum strength is 6,000 pounds. So if you're falling and you got 550 pounds of force, it turns on like that elastic region, slows you down slowly, and it won't break until you reach 6,000 pounds. I don't think anybody's going to fall so far that the force to stop them would be 6,000 pounds.
Would there be like an easy way for you to like figure that out? Like someone just like another like 150 pounds or whatever. Like how far would they have to fall before they would hit the 6,000 pounds?
Yeah, you could.
I didn't know what.
Right? F equals ma. Right? If you know their mass and how much they're accelerating.
But how would you figure out how fast they're accelerating?
So this you got to combine a lot of stuff here.
Oh, yeah, because you're also taking into account that.
You got drag, so you would want terminal velocity. The maximum velocity would be the worst case scenario. You'd have to figure that out, and you'd have to look at how much energy you would have. You can look at how much work gravity does or the rope does against you, and then work is force times distance. So you can calculate it that way. So I want to take time to do that. That's a good question because you'd pull a lot of concepts to answer that question. You could do it for sure. Okay, here's a good question. Wait. There. Think about which had the larger impulse. I already asked you this and answered it. You notice the bottom, they stop. Oh, I was kind of
Yeah,
in the
you were
way.
standing there.
Why didn't nobody say nothing?
Because we didn't know
We've
we
been
were
on there
something there.
Ah, sorry. Two cars, identical velocity. Notice, this one starts braking, that one hits a brick wall.
Stop at the same spot.
Stop and think about who had the larger impulse.
If they stop at the same spot,
The
they're the
car.
same speed, then equal.
They're equal. Their initial momentum, they had the same mass, same velocity. They both stopped. The change in momentum was the same for both of them. The change in momentum is the impulse. However, they accomplished that differently. It was the same impulse, but Trevor, go ahead. Bottom had a larger force. Why do you say that? Yeah, that's a quick stop. Little force, big force, little time. That one hurts. This one, walk in the park. That force doesn't hurt at all. Even if I apply it for 10 seconds, I don't care. So the top one had the larger time for that impulse. I want you to pay attention to the timing. Watch how long it takes both of them to stop. They're almost exactly the same. Almost. They're very, very close. Let's assume that they came to a stop in the same amount of time. Well, generically, who had the larger impulse?
They're the same.
They're the same. They both had the same mass, same velocity. They both came to a standstill. They both changed their momentum the same amount. Are their impulses different?
No.
I'm telling you, let's assume they both came to a stop in the same amount of time.
Then their force would have to be close up.
Their forces were the same. Same impulse, and it was accomplished in the same way. This is why cars are made to crumple. Did you guys know that?
I didn't know.
Your car is made to crumple on impact.
I knew that with sports cars, the cars that are designed to go really fast. I knew that
Yep.
they crumple easier because the wheel's supposed to protect you
Yeah,
in an accident.
and now you know why.
But I didn't know that normal vehicles.
Yeah, all pedestrian cars. The crumpling elongates the time of your impulse. If it takes longer for your collision to happen, that means there's less force.
Is that why the materials they use to make them are more cheaper? Because if you use a stiffer material, it would be harder to crumple.
Correct.
So if
They do not only the design, the shape, but also the materials.
Because that's what it seems like the materials. If you had a vehicle from 60 years ago.
Yeah, I mean, part of that is other considerations.
Yeah, I'm just saying, if it had the same safety features, just minus the crumpling, wouldn't it still? You would still be more jarred by that because.
Yeah, and they think about that,
Okay.
right?
At the same time, you don't want something that's so it's going to go right through the car.
Right.
So
Yeah.
It should be
But
separate
I
from-
want to point out, do you guys know the Tesla Model Y? Wait, no, Model X, the SUV. Did you know, I'm almost positive that has a perfect 5-star crash test rating, which is extremely rare, right? You know the crash test ratings?
No.
They tell you how safe this car is in an accident. One of the reasons that the Tesla Model X has such a good crash test rating is because there's no engine in the front. That whole thing, they can allow to be a giant crumple zone. Right? Your trunk is in the front of a Tesla.
What if you get hit in the back though?
The same thing. That they don't have any transmissions or nothing. They have more space. They build more crumple zones. But particularly, think about the front. You have a huge empty space. You don't have to put an engine there. So you got the freedom, hey, let's make this thing a huge crumple zone. Right? When it hits head-on collision, you have a ton of time for that front to crumple before the car actually hits the unibody. I don't want to get too technical. Until you experience a collision, a lot more time to crumple, less force, safer.
So the highest crash test ratings ever.
In the Tesla Model X?
Yeah.
Yes, it's
No.
unbelievable.
They
All
have
around, too.
five stars in every category.
Yep, it's incredible, right? So I encourage you, like, go check it out. Like, you can watch the videos. Another quick thing, the battery pack in Teslas, they're all in the floor. It's in the very, very bottom of the car. That means all of your weight is really low. If you watch the car test, they slide the car on a rail, and then it stops, and it skids off and hits sand. It's testing how much the car rolls. Rolling is bad. The Tesla has so much weight down low that when it rolls, the weight's at the bottom, it pulls it back down, and it doesn't roll. It's a huge
If you
benefit.
hit it hard enough, it will roll.
It will, yes, but it's extremely difficult. So anyway, I don't want to talk about that much more.
Like, compared to if you had a Wrangler, that thing would just roll for days.
Oh yeah, Jeeps are notorious, especially when people lift them, they make it even worse. But anyway, here's another example. An impulse happened. When you kick a football, does that happen quickly or slowly? Quickly. Really fast. Right? The reason that this ball crumples so much is you have to have a huge force really quickly to get that ball enough momentum to kick. No, I don't think it is. I'm serious.
That's on.
Right?
Yeah, exactly.
This is something that happens normally. I can almost guarantee you. Right? Has anybody ever seen a golf ball hit in slow motion? It literally squishes like an egg before it rebounds. Right? You never see it. It happens so fast, but
What about a baseball?
impacts have enormous energy. I'm almost sure baseballs do as well.
Yeah.
We can look some up. Huh?
I've seen one with the soccer ball.
Soccer ball? Does it deform like this? Yeah. Aiden, we'll look some up if we have time, but it's crazy. Does anybody know what these are?
Oh, yeah, those are the barricades, but they're full of water. aren't
They're
they?
full of water.
Yeah.
Why? Why are these there? Why
So
do
if
they
you
exist?
If you hit them, they are going to compress when, like, if you hit a brick, like a cement
Yeah.
wall.
What's right behind all these barrels?
Guardrail.
Steel barricade. Your guardrail. Would you rather hit the end of a barricade or some water-filled cans? Yeah.
Well, don't they usually have those, like,
Basically, not anymore.
don't they usually have those water?
Yeah.
Don't they usually have those water barrels? Don't they usually have them, like, right when a rail would start, so to prevent anyone from hitting it head on?
Yeah, that's why. Right? They protect a car from hitting and just like piercing your car.
Because they would just demolish your car.
Because you have a lot of speed, you got to have a huge change of momentum.
Yeah.
Now, you got to have one impulse. It's going to bring you to a stop. I would rather have a really small force, have it take a long time to collide and bring me to a stop, rather than hitting that guardrail and just stopping me dead.
But they don't
Both
have
of
to-
them are going to stop you,
they don't
but
have to worry about those, like if it was just a long, like if you're like in the middle of the road,
Well, like this.
you would hit
You might
them.
just be dead. And
yeah, bad news.
So yeah,
Right.
one might
Huh?
actually do feel better.
Like so those are
So
like
maybe you
only
should
right
ride
the
the
guardrail
guardrails.
of a rail, so you don't hit it head on.
Because that's one of
Yeah.
the worst collisions.
Compared to if you hit it like on the side, you would just kind of skid along the
Exactly,
side.
exactly. And you could apply the brakes, your car could, yeah. Have you ever seen overpasses? You know how they have the huge concrete pillars to support it?
Yeah.
It's in the middle of the interstate.
Yeah.
They put them in front of those too.
Yeah.
You don't want to be hitting. And have you also noticed most of them should be angled? Right? If I'm driving in the road and my concrete barrier for the overpass is here, the barrels are angled towards me. They're not straight in a line. I'm often not going to hit the concrete pillar right down the middle of the median.
Yeah.
I'm going to veer off. They take that into account to make this angle because that's where you're most likely to hit. They want to give you maximum time to slow down before you actually come to a stop
And then also
so that you experience less force.
would it help
This is
with the
safety
curves
measures.
wouldn't that cause your vehicle to veer off a little bit too, so you might not even hit it completely dead on?
Yeah, it also could. Yeah,
Okay.
it can deter you and pull. Yeah. Okay, I want to keep going. This is something that I'm going to get into a little bit when we talk about the system, right? Your system could be, say, the car. Your system could also be two different cars. We need to realize that momentum is a vector. Mass is a number, right? That won't change. But your momentum is determined by the direction of your velocity. If I'm moving this way, I have a positive momentum. If I'm going the opposite way, my momentum is negative. You need a value and a sign, the direction, for every single momentum. Right? They're different directions. What was the impulse on this car? You saw the car go, it stopped, and then went the other direction. Think about it carefully. The impulse is the change in momentum. I had positive 30,000 this way initially. What did I end up with? Negative. All right, do your math. What's the final velocity? Final velocity is negative 30,000. To find the difference of something, I always do final minus initial. Negative 30,000 minus 30,000. Negatives. No.
Oh, yeah.
Minus 30,000 is the final momentum. I got to subtract the initial. Well, subtracting 30,000, I get negative 60,000. Does that make sense?
Yes.
I was going this way, and it pushed me back the opposite direction. Not only did I stop, my momentum decreased by 30,000. I also went the other way. There was 30,000 more momentum added. Here's a line graph to look at that. You went from here all the way over here. The total momentum, or the total change in momentum, 60,000 Newton seconds. All right, think about this one. Okay, so you got a ball, 10 kilogram meter per second of momentum. Hits the spring, and then goes the other way with negative 10. What's your total change in momentum? Negative 20. Right? I subtracted 20 to come to the standstill, and then I added a negative 20 to get up to this momentum. Or negative 10, excuse me. My change in momentum was negative 20 kilogram meter per second. Down here, what was the change? Negative 10. It just stopped. So, who had the larger impulse? The top one. A collision that rebounds has more damage unless you can really increase that time. Because you're not only stopping the object, but you're pushing it back the other direction. That's way harder to do than just stopping something. All right? Again, the change in momentum is the impulse. So I can learn both of them. Okay, remember, I just said, we just showed, if you have a collision that rebounds, that takes a lot more change in momentum than just a dead stop. So say you roll a ball, hits a wall, stops. We had some force applied over a certain amount of time to create an impulse. That's what took the momentum out of that system. What if I got a bouncy ball?
Yep.
Right? Not only did that ball stop, but it was pushed back the other direction. I had twice as much impulse here because it came in with momentum and stopped and then went back with opposite momentum. That takes twice as much change as just stopping. This is more dangerous. This is an interesting one. It's a little bit counterintuitive. You jump out of this, it looks like a motel or something, I don't even know. You jump off, there's a fire. If you want to minimize the impulse on your body, which one do you choose?
No, the impulse going to make you choose the math. But I feel like the trampoline would still give
Neither,
you
you
less.
fall in the middle.
Trampoline is
Trampoline
Two.
high risk, high reward.
Okay, so first question, my specific question. Do you want to reduce the impulse?
Just reducing impulse, the math.
The mat. Why?
Because the trampoline is going to stop you and then shove you back up, and then that's going to subtract, and it's going to give you even bigger impulse.
Yes.
And now
What
it's just
is-
going to stop.
Assuming a
Wait, don't do hypotheticals. Just stick with me, please. Ethan's right. The change of momentum is whatever you fall off with to stop. That's it. Trampoline has to stop you, and it bounces you back up.
and you're assuming you're not going to just hit the floor on that.
Correct, yep. However, does that mean that this one hurts more?
No, it hurts less. Most of the time.
It might actually hurt the same. Because if I do exactly twice as much impulse, it might take twice as much time, so my force is the same in both scenarios, right? That takes a lot more to think about. We'd have to look at like the coefficient of elasticity, all that stuff. But again, the impulse, this is a smaller change in momentum than bouncing and coming back. Therefore, that has less impulse. All right? So, I want to pause there and then... Oh. Okay, so systems, this should be easy. We talk about systems all the time. What is an open system? Good. Open. Like I said, hey, yeah, when you got an open system, mass can come in or out of your system, and energy could also come in or out. Now, this could happen by work. You could do work on a system, apply a force, and change energy. In momentum, when we're looking at momentum, an open system would be one where you could lose momentum. Right? You could have a force act on the system and pull momentum out or put it into the system. A closed system. That's the best way to, like, super simple summarize. If you have a closed system, that means mass isn't going in or out. You're not having objects enter the system boundary. Objects aren't being ejected from your system boundary. They stay in there. And there's no forces being applied. There's no forces being applied out of the system. So in this situation, momentum has to be conserved. Everything's staying inside. The ultimate step would be an isolated system. Meaning absolutely no forces, nothing possibly leaves the system. In the real world, we rarely have that. Right? But that's what a system is. Now, I want to give you a scenario. What happens? Again, I'm going to draw the greatest car you've ever seen in your life.
Yes. Look at the aerodynamics on that bad boy.
Oh, yeah. This is car number 1.
Still better than a Ford.
Wow.
Well, Chevys tend to be lighter because they're.
This is the second greatest drawing of a car you guys have ever seen in your lives.
Obviously.
Of course.
Alright, no one's off.
Behind the wheel and O2.
Mario Kart special with a entrance block.
Alright. So, situation 1. If system equals car 1, then what is the change in momentum? So really got to pause and think about, okay, scenario 1. That is my system. Okay, first of all, think about what happens. These cars have equal and opposite momentums. What happens when they collide? Do they stick and stop? Does one push the other way? What happens? Exactly the same amount of momentum.
They're just going to run into each other and collide and stop.
Do you guys see that? Positive 10,000, minus 10,000. They're equal and opposite. They negate each other.
Yeah,
You're going to collide and stop. So, what's the final momentum? P final minus P initial. What's the final momentum of just car 1 after it collides? 0. It gets stopped dead in its tracks. 0 minus, what's the initial?
10,000.
10,000.
Negative.
So your answer, I'm running out of room, but kilogram. If this is my system, that's my change in momentum. Do you guys notice? I lost momentum. Momentum left my system. I started with 10,000, and then it came to a standstill. I had none. Is this an open or a closed system?
It's an open system.
It's open. Something acted on this car, this system, and changed it. You see that? All right, I want to give you another one. What happens? Oops. What happens if that is my system? System is, 1 plus 2.
Wouldn't you have no change in momentum? Because to start off, the whole system is moving exactly equal towards each other. So it's going to be 0 when you have it together. 10,000 plus negative 10,000. And then when they stop, it's 0 plus 0.
I like this. Do we all agree with Ethan? Maggie was saying the same thing, 0. Do we agree and understand why? Because I would agree. I think that's the scientifically correct answer, but it's important to understand why. Why does our system and what we know about momentum tell us that that's true? Well, Ethan was talking about initially, no, you did initially. So what's my initial velocity? Momentum?
It's 0.
Is 0. Why do you say that?
Because the center of the system never changes. Because
Ah.
this dude is 10,000 and that's negative 10,000. So you add them together, it's just
So that's a good point. He is saying, hey, total system, you guys got this. You got one system. Add up all the momentums in your system. I got 10,000 plus negative 10,000. I got nothing. That is my initial, right? Momentum initial. After they collide, you guys told me, hey, their momentums are equal and opposite. They cancel each other out. I'm at a dead standstill. Each car now has 0 momentum. So guess what 0 plus 0 is?
0.
So the change of momentum for that system is 0. Is that an open or a closed system? It's closed. You don't lose momentum. You could also think about it with kinetic energy. 1/2 mv squared, 1/2 mv squared. They're equal and opposite. Initially there's 0. Finally there's 0. You don't lose any energy. That's what a closed system is. I do this to say, hey, this is the exact same physics scenario. I changed nothing about the scenario except how I defined my system.
Systems,
How you define the system changes your answer. It's the same question. They are going to try and trick you. They're going to try and say, hey, what is the change in momentum of the car A system or car 1 system? You need to understand, just look at this and calculate the change in momentum. They might ask you in exactly the same question again later, same problem, but they're going to say, hey, what was the change in momentum of the car 1-2 system? Your answer is completely different. So one, I want to show you that they will try to use this, the system boundary, to trick you, or they will ask you, here's the answer, what was the system chosen? And you have to think, oh, crap. What system did they choose to get this answer? Right? They will try to use that to trick you. You also need to know your system boundary is important. It literally changes the question itself. Okay? So, the rest of class, right, I want, if you go on Classroom, did I not post it? I haven't posted it yet. Give me 1 second. Oh, it's been a long week. I'm behind. Oh, savage.
Who?
Where is my...
What number is it? Oh, yeah. It's something random.
Alright, I'm going to have to change the settings later. I apologize, I didn't have this queued up, ready to go for you.
That's okay, we don't have to do anything.
No, it's not that bad. A lot of it's review. This is like what we started with momentum. I want you all to, again, you'll have to refresh Classroom. Each of you, we're going to do a PhET Collision Lab. There's a cool simulation that shows the ideal collision is using like 2 balls. And you can change like, oh, are they bouncy balls? Are they like steel? Right? It can change how the collision happens. I want you to work through, I tried to simplify this to talk about inelastic and elastic collisions. What do you think happens in an elastic? When you have an elastic collision, what happens in that collision? They bounce off. Right? Think of 2 bouncy balls. When they roll into each other, they bounce away. That's what an elastic collision is. What do you think the opposite of an elastic collision is?
Steel.
Static. What's the opposite of elastic?
Stiff.
Inelastic.
Oh, okay, okay.
What happens in an inelastic collision? If an elastic collision bounces, what happens in an elastic? Stop. That's what this was. An inelastic collision is where you collide and stick together. There's no ricocheting, so whatever momentum, whoever has more, they win. Right? So that's to give you a little context. This lab, there's the link directly above. I would click the HTML5 option. Like mine, it won't let me play this, so I don't even deal with it. I would choose, guys, everyone, I want you to see this. Choose this HTML5 link. It's in, oh, for goodness sakes. Don't tell me that I'm talking like a madman.
Sometimes we're quiet, sometimes we're not.
I know. Usually you guys are pretty quiet. I don't necessarily like it.
I thought maybe
Because then I can't tell if we get it.
I thought maybe I missed something. I didn't want to be like, what are you talking about?
No, call me out on stuff, right? I don't want to mislead you. I don't want to take a minute to talk about something that you guys are like, wait, what are we talking about? So, when you click this link, What?
That's me every class.
That's not good.
A little bit. But specifically when I'm teaching. Does everybody see this? I want you to do this HTML5 link. This one I don't think will work. Don't even try it. It's the new version, right? It's a new code they use. It's in beta. I haven't experienced any issues. It's a prototype, but you're going to open this lab. And the intro is just fine. Do you guys see this? There's a lot of settings you can change. You can throw in arrows to describe the momentum. The change of momentum can be labeled, center mass, all sorts of stuff. And you can say, hey, I want these objects to have the same mass, but I want different velocities. And you can literally watch what happens in that collision. You can also reset it and say, hey, I don't want them to bounce off each other, which is an elastic collision. I want them to stick together. So I can go and say, hey, 0% elastic, a completely inelastic collision. When they hit, they stick together, and now whoever had more momentum, they win. So you can kind of watch what happens in different collisions with different momentums and different types, an elastic versus inelastic. The first scenario is looking at elastic with equal mass. So you would have to go and say, okay, completely elastic, and I want the same mass. I need to make them equal masses. And you got to make a guess. I want you to please make your guess before you run it. I don't care if your guess is right or wrong, but it's important to use what you do know to make a guess and then see if your guess holds true. If it doesn't, you got to figure out, why was I thinking about this wrong? What am I missing? Oh, crap. I forgot that they have the same mass. Of course they would do this, whatever. Then I want you to collect some data, right? Have the same mass and give one of them a huge velocity, right? You can control the velocity right now. What happens if I double the velocity, right? Give me, I don't know, 3 or 4 measurements. Just run 3 or 4 scenarios and get some data. Talk about the momentum before and after. So this is good practice. How do you collect data, right? What is the relationship? Initial and final total momentums. You actually have a diagram that's pretty handy to help you. It shows you the total before and after. That's going to be pretty handy. And then the last thing is, just describing what you're seeing. Then do the same thing, but I want you to take different masses. What if you got one of the balls that's twice as big? What happens to the collisions? Does anything change? Repeat the same process. Part 2, you get to experiment. Pick up your own scenario. Make up whatever you want. I'm forcing you to do one of the scenarios, be completely inelastic, where they stick together, and they have equal mass. This scenario, you could do whatever you want. Same mass, elastic. Actually, we already did that. Same mass, inelastic. Double the mass. 50% inelastic, doesn't matter. Get some numbers. Again, give me like 3 data points for each. Just run 3 trials for situation 1. 3 for situation 2. 3 here, 3 here. It's not a lot. It won't take long. Just set the variables and run it, and then record your variables. And then I don't like that wording I put. Same thing. I want you to make a guess before you start. Predict what you think will happen. Get data. Figure out what does happen. And then tell me, hey, what the heck's happening? And tell me why. Finally, give me main ideas. A lot of these you probably already know and we've already talked about. But this lab should reinforce them, especially from what you see. All right? My knee. Again, I want the rest of the class to work on this. We can take a little bit of time to finish it on Tuesday, but I would like you to do this as homework. I want you to get it, right? We're not going to have a lot of time Tuesday. I mean, like maybe 20 minutes before we got to move on to other stuff, right? We got to keep on pace. So whatever you don't finish, just wrap it up as homework. It's not a big deal, right? Don't be stressed about this. It'll go a lot quicker than you think. I want to give you the rest of the time to work on it. What are you laughing at? Huh? Why?
Really?
I mean, I can help you. I'll help you figure out if you're not sure like what to do. Basically, once you get to scenario 1, you do the same thing, just tweak some variables. All right? Again, this is nothing new, except you're actually going to be witnessing collisions. So I'm trying to bridge. We've talked about momentum, impulse, a little bit about collisions, thinking about change of momentums. I want to bring that into, okay, watch some actual collisions, try and predict what you think will happen, and then look at what actually happens, and then start to think about, oh, that's why they bounced off each other. They were equal and opposite, but they were elastic, stuff like that. I'm trying to bridge two things in this activity. All right, again, same thing. I did it electronically. I know you guys aren't a huge fan of doing everything on the computer. I think you might have, huh?
I actually really like it.
I know. I was gonna print these out. Honestly, this week was awful for me, so I ran out of time. And two, it's really easy for me to make this one document and just put it on Classroom, and then you guys just submit it. Because otherwise, I gotta go print them, then I gotta grade them manually. So I apologize. I'll try and do that more in the future to like print it out for you guys. I know you've expressed. That's why I print the test for you. I'd like to do them on Google Forms. It'd be easier, but I don't want to make it difficult for you.
Thank you.
I'm also, you're welcome. Appreciate that. I also am not 100% sure. Has anybody heard what is the format for your AP test in May? Do you know if it will be pen paper? I don't know.
I think they're trying to make it back to paper.
I want it to be paper.
The last I heard, that's what they were intending, is to make it pen and paper. They might do virtual for extenuating circumstances.
We have the mock exams.
I don't have control.
We have mock exams like
100%.
several months before.
Yes.
So I kind of see where you're at.
Yes.
And I was confident on those, and then I only passed 1 of 3. And then
On the AP test?
yeah, the actual AP test, I only passed 1 of 3.
What do you think changed?
What?
Like, what do you think happened? Was like the AP just way harder, or?
I took
It
away
sucks,
my
it's
best
digital.
field, the multiple choice.
Yeah, it's all digital. It's running.
Yeah, because
Oh, you guys
I
probably
passed the mock exam simply by multiple choice.
Yeah, because you
I
got
took it away.
stupid
You
numbers.
also got to use notes.
I am
You don't
still
have
salty that
time
I
to
got
look at notes,
screwed
though.
over during AP line.
Are you talking about for Lent?
That would be really
Yeah,
annoying.
Still
I
no,
literally
because the
used
whole year
my
we were
note
told.
paper to write my first paragraph.
Did you pass?
Yes, I got a 4 and I wrote it
Nope.
in 10 minutes.
Dang, what a dog.
It's a
I took the whole thing.
I got
Yeah.
screwed in AP line.
Sorry,
I was like, I don't want to
Notes.
interrupt.
you could have. You could have.
I didn't want to. I just.
You're good. All right. So I want you to get started on this. Please let me know now if you have questions. Ask me now, because granted, you can email me, but I'm not right here. I want to get you started. Make sure you know what to do. Turn you loose. That way, if you don't finish, just wrap it up on the weekend. All right. Let me stop this quick.
It's gonna be some old text.